So we'll talk about Pbr material. So what is Pbr, and generally what are different material types? So basically each rendering engine has its own way of describing materials. A material is a mixture of different textures. Always some procedurally generated stuff. But for gaming people, we will consider most of the things as a texture. So from all times, we were using all sorts of renderers. Let's say in Maya, we used to have Mental Ray, a third-party renderer that I don't know who developed, somebody in Berlin, and then NVIDIA bought it, and then they discontinued it. So Autodesk is always including some, some additional renderers. So Maya has a hardware renderer. It has a software renderer. Those are kind of, well, I wouldn't say stupid, but let's say you would always want to have a high-end renderer, or like these days we have Arnold. And there are different renderers. So we have Arnold, we have, what is it, Mental Ray, I think. Architects love Mental Ray. There is RenderMan, Pixel, what is it, Pixar. Pixar has their own rendering engine. Anyway, there are lots and lots of different rendering engines. And they require their own materials. So they might have very different maps and things that create the materials in order for that renderer to work. But basically from I don't know, like 5 years, there was a kind of push in industry, especially in gaming industry, but it kind of goes down to all other areas in VFX industry. So this PBR idea, physically based rendering. So the idea here is that we want to have a set of materials, set of textures that would work the same way in Unreal, they would work the same in Unity, and so on. So let's look at Unity. This is Unity and its material. You see we have Albedo, we have metallic, we have normal map, and then we have other things, detail map, occlusion, height map. But the idea here is that we try to standardize things. So if I go to Unreal, you see base color. That's the same as Albedo in Unity. So we have metallic, roughness, normal, things like that. So we try to kind of make it, to combine, to have the same set of materials. So what are they? So basically, first let's look at base color. It's let's see 2D and 3D. So you see here we have a 3D object, and this is a color texture. So in this file, we should have only the color without any information about lighting. So technically, this part right here, the bottom of the foot of the, how's it called, a teapot, it's probably wrong because it has too much shadow here. So it's probably not part of the color, it's probably actual shadow, so it's not perfect. And of course, this is a photogrammetry model, so nobody will be wasting time to remove it here, because it's most likely will be there anyways, and probably there inside, where this handle connects, probably is also too dark in this channel that it shouldn't be. But regardless, more or less, it's a color map. So let's see other models. Again, some scanned data. Color, just color information. So hopefully there is no detail of lighting at all. Nothing from, it should be only the color data. This is not, but let's say here, you see how ugly the model looks like? It's only a color. So we shouldn't have any detail of that includes reflections, lighting, or anything like that. Right, so that's Albedo, or old school way is to call it diffuse color. Of course, diffuse, it doesn't refer that, it might have reflections and whatnot included in it, but our idea here that we are using Albedo, base color, whatever you call it, but what we want is only the color information in this channel. The next one is Mettalness. So the Mettalness is fun. This one doesn't have much information on Mettalness, but this girl does. So with her armor, you see, everything is black. Everything is black except her armor, because the armor is metallic. And basically, if we go to Unity's description, Unity blog, and talking about PBR, physically based shading, physically based rendering. It's the same thing. We will have this diagram right here. So where is it? Metallic value charts. So basically, we define materials in two things: metals and non-metals. And basically, white in this channel would represent that the object is metallic, and black that it's not metallic. And what are the metallic objects? It's the ones that have a reflection, that have a strong mirror-like reflection. So let's say, yeah, if I would need to make I don't know, a mirror, that would be perfect white in Mettalness. If I would need to make a wet surface or water, that would also be metallic. Of course, technically it's more complicated, and it talks about the way that the light is being reflected in the edges and corners of the object. But we won't go that far. No more examples here. Yeah, basically the metallic ones will have a strong mirror-like reflection here, while the non-metallic surfaces won't have that. I don't see any more examples here. Regardless, just to have basic things. So if you think your object needs to have reflection, the metals do, you will have a white texture. Why it's not just white? Why do we have this weird black, not black, gray stuff? So of course your armor might be dirty, and the dirt has different type of reflectivity. It's not reflecting that much, or maybe it's worn and somewhere it's polished because it rubs to things, white, and somewhere else maybe it got rusty. Rust is no more. It's no more metal. It's becoming different properties, and it doesn't reflect that much. So this is our Mettalness. Usually it's called Mettalness, and let's say in Unity you have two workflows. Even the Pbr has two workflows: the metallic one and the how's it called? What's the name? And specular. So then there is different ways of implementation, but let's just go with the default, so to speak. So Mettalness. Now the next one is very interesting. It's Ruffnes. What the hell is a Ruffnes? So basically, imagine you have a very polished material. So basically, this Mettalness refers to how the light is reflected, and yeah, it is a metallic surface, so it has mirror-like reflections. But imagine you have a metal, but it's very, no, let's go with something else. Let's imagine you just take any sort of object and you brush it with a very fine, brush, and its surface becomes totally flat, and therefore. So in the Ruffnes, you would have, I think, white for this, and it should, let's see what it does. Yeah, I think where it's white, it should reflect less. Let me see. Yeah, here it's white in the Ruffnes, and the final rendering, you see it doesn't have strong highlights on it. So what is going on here? So basically Ruffnes, imagine any type of surface, if you talk about its microstructure. Paintbrush. So how do I draw here? Size. Yes. So imagine you have a totally flat surface, and the one would have micro, surface details. When you touch it with finger, it still might be smooth because it's way smaller roughness. And you have lighting that comes in one direction. It will always bounce back in, I don't know, angle here, but basically it will bounce in the same angle. And therefore what we will see is we will see these nice shiny highlights, probably highlights they are called. What happens with our rough surface, where we have lots of roughness? So one light source, one light ray comes in like this, it might be reflected this way. But here it reflects something different, and here it reflects to different area because of the rough surface. So basically, it's all scattered, and we don't get this mirror-like reflection. So we won't see our face basically here, even though we might still have the highlight, this highlight. So basically, how do you use it in practice? So where you want things to be really reflective and really mirror like flat kind of things, you have it white, and where it's black, it's a very rough surface. So even let's say piece of wood could have let's say it's with I forgot the word in English. Okay, let's ignore that. Let's have a look at some more examples. Okay, this one won't have. So roughness. Here, again, let's see the final renderer. So let's look at the highlight of our teapot here. You see I'm turning around the light source, and it has the highlight here. But the handle, it doesn't. You see it's totally scattered. There is no, you couldn't, even you can obviously say what's the direction of the light, but you cannot say where it hits exactly the surface, 90 degrees. So that's 90 degrees from a light source, you get the highlight here. So what's going on here? Again, we go back to roughness. So in this case, it's opposite. So black is probably then non-rough, and white is a rough. So rough means the highlight is not like here, it's scattered, so to speak. All right, so then we have normal map. And what is a normal map? So again, it's the same thing as a bump map. You might have seen bump in old school games, and basically it kind of tries to fake. It tries to fake surface details that don't exist in actual model. So let's see if we have something like that here. So of course we use normal map here, and old school bump map. I don't have any examples here right now with me. But basically what it does, imagine we have a surface, and that's how we want our surface to look like. So we have just one polygon. Actually, I will go back to Maya here. Oh, that's not Maya. And I will create a sphere. And our sphere is smooth. But how could it be? It has flat polygons here. So if I go to edges and say I want all my edges to be hard edges, now it actually renders it correctly. So before we were faking. I want to deselect it. So now it's actually a true representation of our model, because they are actually flat polygons here. So how on earth do we make it smooth, and how it's connected to normal map and bump maps? So let me go back out, make half of it smooth. So soften edge. Okay, so how does it do? Basically, imagine we have this polygon. This is a vertex, and a polygon, and the same situation here. And when we have a light source, it comes here, bounces back, and basically we get a value of this pixel here when it's projected on the camera surface, or rendering surface, whatever it's called. Basically, we get an intensity of two things. First, we have a color of our object. So in the Maya example here, we just have gray. And I don't know where our light source is here, but it's somewhere. And we have, and we get back the value. And if, let's say, we have a polygonal surface, so this is 3 polygons, and the same light source, I'll pick a different color. So let's say our light source is here, it comes here, here it comes in a different angle, and here it comes in totally different angle. And based on this angle, we get lots of light here, medium, not so much light here, and we hardly get, maybe it's any light, because of course there is no light at all here. So basically we should then get different values, color values, and basically that's what we get here. You see it's, we see actual geometry because how the model is created. But what we could do instead, because we are not calculating just this area, we are calculating pixel, each pixel here. And basically we could take a polygon's normal, and a normal is just a vector perpendicular to our polygon. So polygon, there's a vector, it's 90 degrees, that's our polygon normal. And this polygon has this normal, and this normal. And actually, when you calculate the lighting, you calculate the direction of light to this polygon normal. But what we can do if we want to make a smooth surface, we can fake this normal, and we see, okay, this neighboring polygon has a normal which direction is different, and each time we're going closer to this new polygon, we will take an average of the normal. So by this taking average of normals, we are faking it, and we are making this smooth shading. Now, if we add a texture here, which affects the way our normals, the way our normals point. So let's say here the same example, but I will, make a texture on top of it where we have black parts and white parts, and black parts and white parts, black parts. So let's pretend that the black part is up, and to represent that sort of surface, it might be up, other way around, and there's a gradient here. So basically we get normal like this, normal like that, normal like this, normal like that, like this, and this is how we fake our irregularities of the surface, our bump map. So let us see, can I find something? Bump map, paper, I'm not sure how to find it. Let's go to Google. So I think it's about 80s that the first papers about bump mapping are written. And you see this Fong, it's a surname, right? If we go to Maya, that's not Maya. If we go to Maya and say, I want to assign a new material, what sort do you want the Fong material? So Blin, Lambert, Fong, they are surnames actually of people who invented these things. Okay, so can we see the original paper of Boy Tong Fong or whatever his name is? I don't know. Let's see the Wikipedia article. Okay, I'm not sure I will be able to find the original paper. But basically what I'm trying to say is that we have lots of things coming from old history that are still here with us. Yeah, Utah University. In 3D Max, we have Utah Teapot as a 3D object. Again, comes from this university, all the same stuff here. Yeah. So this is old school 3D graphics, and this is actually how you calculate those things. This is, whatever, I don't understand any of that. It's too much math for me. But this is basically the history. And therefore you have Fong material here. Okay, so we go back to our bump map. So this is, how we kind of fake our surface irregularities. So when it's good to use, imagine you have a wall that you could use just one polygon to create the whole wall, right? Room wall, but maybe it has a plaster, it has I don't know what surface material is created, but let's say it's plaster, and it has a small bumps and irregularities of surface, but you don't want to actually model it and have polygons of that, and that's where the bump map comes in. So but why we are talking about normal maps and why they look this wonderful color here? So basically that's the old school way, is bump maps. Remember that in image, when we create an image, any JPEG or whatever has RGB colors. So in our channel, we have from 0 to 255, I think, colors. The same goes for green, red, green, blue, all 3 channels. So there are 3 black and white images with values from 0 to 255, 255 being white and 0 being black. So what can we get from those 3? Basically, we can not only have up and information of up and down of the object, but also, left and right, because, X, Y, Z. So basically that's the idea. We have a way more complex information of surface irregularities from normal maps. And it's not so easy to draw them. I mean, it's possible to draw them in Photoshop if you just want a bump, like that sort of thing. You could do it. technically. It's very hard, we could do it. But normally what we do is basically we sculpt a high poly model, and then we transfer textures to low poly model. We can do it here in Maya with, if we have two models. Let me try just find where it is. Texture transfer, I think it's called in Maya. And I have no idea where it lives. Texture transfer. Anyway, it should be somewhere here. We'll be looking at it later. But again, we would need to have a high poly version of our model. And to do that, it's way easier to do it with sculpting. And that's why we are downloading Moodbox in this case. I'll just create a new thing, new scene, base head. Let's turn this off. And we go to sculpting, sculpt. And grab a, oh no, I'm not gonna paint, I need to sculpt. Sculpt. Okay, let's subdivide it. Oh, Shift D was it? And I need to render it normally. Yeah, great. Okay, so now we are sculpting, and basically it's easy to create all sorts of surface detail with sculpting. Of course, we have some tools here in Maya as well. You know, we can subdivide our object free, and the actual to I don't remember how to do it. That's under modeling. Anyways, you have some sculpting tools here. You would need just way more dense mesh. We talked about it last time, I think. So, but with Moodbox, we can jump into detail into the levels of sculpting. So where is it? Let's subdivide it more. Shift D. We have 5 subdivision levels. We can go up and down with those levels, and the highest level will let us have, that's 0. Will let us have way more detail here in the sculpting. And it will be easy here in Moodbox to transfer, again, maps high poly to low poly. And the result will be the surface detail, which doesn't exist in our model. You see, it really looks like this armor here is extruded. Let's see if it is really extruded, wireframe. Not really, right? It's just a flat area here. But if we look at final render, let's add actually wireframe so we can see how to do it. I forgot how to do it. Oh yeah, right, like this. So you see actual geometry, right? This thing here, it doesn't exist in geometry, but it looks as if it's you know, it's a surface detail. So we can have lots of nice things here, you know, surface irregularities with a normal map. Okay, so we talked about Metalness, about Ruffnes, about normal map. AO, again, maybe it's not directly a part of Pbr material, but everybody uses. What is AO? It's Ambient Occlusion. And what do you have here is basically, like, if you would have enough time to render properly things, you would never use AO. It's a fake thing, you hate it. But you have, you know, 2 hours for your one frame to render. You are happy, you hit render, you go to eat, and then you come back and you have nice image rendered. But you are playing a game and you want to have 60 frames per second rendered. So we don't have enough time to actually retrace all the shadows because it's just computationally heavy thing to do. So what do? We make kind of a statistical image which represents where most likely the shadows will be. So according to how it's done, we just have lots of light sources, we shine, and where it's not, where we have less light, we just draw it black. And most likely it will be black. Of course, we can have a situation where this would fail. Imagine I have a flashlight and I'm shining inside the mouth of our teapot here. So of course, ambient occlusion map will tell us it's shadow here, and our final render will have still darker here than it's supposed to be because we have a direct light into the nose of our teapot. So it's kind of a fake thing, but it works most of the time. And that's the one more important thing. Again, it's not part of PBR specifically, but that's also very important for how we render our here's. So usually, if we look at polygons here, let me just have a base color. No, let's have just, I don't know, which one. Yeah, it forces, oh yeah, it still forces us to see, still shows opacity. Okay, so let's actually, we'll need to imagine here a little bit. So here you see those hair strands. They are actually polygons, and there is nothing that that really renders. I mean, there is nothing in polygons that renders separate hairs, separate hair. It's actually all in opacity channel. So you see black is invisible, white is visible, and only here has it. Maybe something else? No, nothing else in this model. So here in this model, we go to opacity. Oh yeah, this is something else. Okay, let's ignore that. And no other model I have here at the moment uses opacity. Let me find something more. Collections. Characters. Where we would find some opacity. No. Maybe we won't find it just so fast. But you know, the idea that is you're using it mostly for the here, anything that has to be transparent, but you don't want to actually model it as such. So yeah, the here is a perfect example. I don't seem to have more. Oh yeah, this one. Let's see how it's created. I'm not sure if that's the correct one. You see, it looks like, of course, you know, we have empty here, empty sides. You know, it's empty. Anyways, I'm not sure how to say it in words. If we look at the wireframe, and oh, actually, this is done differently. Sorry, this is a wrong example. Maybe here. I'm expecting those horns to be made with. Oh, yeah, the leaves definitely. Not definitely. Let's double check that. I'm wrong. Sorry, wireframe. Yeah, you see, these are just 1, 2, 3, 4 polygons here. If you count triangulated versions, it's a bit more. But this is a polygon, it's a flat thing, and if we apply opacity, it's invisible here. And that's how we create a detail that doesn't exist in our actual model. You know, if we look at our wireframe, huge polygons here, just one polygon representing whole this area. But if we look at final render, oh, it looks so detailed. So it's all made with opacity map. Again, not directly part of PBR, but that's what we will always want to have. So to recap, base color, let's turn off the rendering of polygons. Yeah, base color is just the color information with nothing else. No reflections, no lighting, no nothing. Metalness, what parts of the object will have metal-like reflection. Roughness, how the light is scattered. So the rougher it is, the more scattered and big highlight is. Big, it means opposite as from small, concentrated, and shiny. Big is very weak, very scattered around kind of highlight. And normal maps for our surface detail, and opacity for mostly these sorts of details.